Hello and welcome to the day 4 of the third week of this lecture series. I hope you guys are doing well, and I also hope that you are following the suggestions that I have been making. Like I guess you have practiced a lot regarding the stereographic projection. If not, then please do it. And at this context, I'll also try to make a note that you can consult the book by Harris and Bertolucci, which was suggested originally for this stereographic projection part, and group multiplication table formation. You can consult any standard book on group theory, any mathematical book, and also you can consult the book by Frank Albert Cotton. So with the knowledge that we have gathered so far, we will now utilize them to form something called representation of a group. Okay. So what do we understand when we say representation of a group? So we have learned to write a group in terms of the symmetry operations. Okay. So when we particularly talk about the symmetry point groups, now we write in terms of, say, all these Swain-Claiss notations like E, Cn, sigma V, sigma H, sigma D, I, Sn, and all those things. So that's fine. Now, if we have to utilize the group theory to understand several molecular property, particularly in the context of the symmetry of the molecule, then we need to have a proper mathematical representation of these symmetry operations. Okay, so what is a way to form a mathematical representation of these symmetry operations? So if you are familiar with quantum mechanics, then you probably know that one of the ways is to utilize matrix. So here, in case of symmetry point groups, we will use matrices to represent the symmetry operations, and thereby we will be representing the whole group by those set of matrices that actually represent the symmetry operations. And then we will use some other properties of those matrix representations to make our life more simple. And so let's try to learn about this representation of the group. And before we go and form the matrices for the symmetry operations and thereby the whole representation of the group in terms of matrix, we will try to learn a little bit thing about matrices, matrix algebra. Many of you already know matrix algebra, but for those who doesn't know matrix algebra, or have learned some time back and wants to have a brush up, then for them we will go through this basic matrix algebra here. So we will give a brief review of matrix algebra in this section. So first we will deal with certain definitions. So first place, we have to know what is a matrix. So if you look at your screen, the definition of a matrix is given there, which says that a matrix is a collection of numbers ordered by rows and columns. Okay, so if you have some numbers, some digits, which are ordered in rows and some columns, so it's an array. And how it is presented is presented in terms of it's like the numbers in rows and columns, they are written within parentheses. Okay, so that's what is also mentioned here, that the elements of the matrix, so all the numbers that are there in any of the rows or columns, they called the elements of the matrix. So all these elements will be in parentheses brackets or braces. So an example is shown here, where this x, which is written in bold term. So normally when you use a symbol for any matrix, then you use either a bold or bold italics or some a particular type of script. Okay, so see, this X is a matrix which is written in this way. So you can see there are two columns, one here, correct, and there are three rows. These two are rows. I'm sorry, and here are the columns. So I have three columns. So this matrix X has two rows and three columns. Now this is a general example of a matrix. Now if by any chance a matrix has n number of rows and n number of columns, that is, the number of rows and number of columns are equal, then we call that matrix as a square matrix. Okay. Now an example of square matrix is given here. A is a square matrix because it has two columns and two rows. So number of columns and rows are equal. So this A is a square matrix. While if I look at the matrix B here, it has two columns but three rows, similar to the example shown on the top. So this B or this X here, they are not square matrices. Okay. Now one more type of matrix that we can think about is a symmetric matrix. So a symmetric matrix is a square matrix in which xij equals to xji. So this I and j are used for noting the rows and columns. So ith row and jth column is given by xij, and jth row and ith column is given by xji. Okay, and x is any element. Okay, so as a whole, any element of a matrix is given by, if the x matrix element is x, then is xij, where I is the row and j is the column. So for all I and j, if this equality holds, that is xij equals to xji, then the matrix is called a square matrix. Okay, so if you look at here, the element say 1 1, okay, corresponding to row 1 column 1 is 9, and the element corresponding to row 1 column 2 is 1. On the other hand, if you look at the matrix B, you will see that the element for which the row 2 column 1, which is just the opposite of the previous example, is the same. So this A is an example of the symmetric matrix, while if you look at the B, then you will say this, this is not equals to this. Okay, so that means here I have 1 2, this is the element 1 2 is not same as 2 1. Okay, but here this 1 2 is equals to 2 1, that is this one. Fine. Some more definitions here. So what is an identity matrix? Identity matrix is that particular matrix for which all the diagonal elements are unity. Okay, so you have rows and columns. So if you go to the along the diagonal, which will be like the element 1 1 and then 2 2 3 3 and so on. Okay, so this, for a square matrix, this is the diagonal, correct? This is just like you take a square and you get a diagonal for that. So along the diagonal, if you look at, you will see that all the elements are unity and rest of the elements are zeros. So this is called identity matrix, and all the time identity matrix is denoted by this symbol I, capital I. Okay, this is a normal convention. Okay, so now if you have two matrices and you want to subtraction or addition with those two matrices, how do you do that? So to add two matrices, you cannot do it with any two matrices. Okay, so they both must have the same number of rows and they both must have the same number of columns. So if I have say 2 by 3 matrix and then I have a 4 by 4 matrix, then I cannot do any kind of subtraction or addition using these two matrices. Okay, the reason will be like this, because for any addition, the elements of two matrices are added together, and this is done by element. Okay, so if I have matrix like here, shown here, so I have like in the first row 1, 9 and minus 2, and on the other hand, other matrix I have 8, minus 4, 3. So I can map 1 to 1. So 1 plus 8, 9 plus minus 4 and minus 2 plus 3. So I can have this 1 to 1 addition or 1 to 1 subtraction. But if I would have a matrix something like 1, 2, 3, 4, 5, 6, 7, 8, 9, I could not add this to this matrix, because the first row, second row would be fine, but the third row it will not work. So I cannot do this element by element addition. So that is a condition of this addition or subtraction, and how you do it I told you, and this is specifically mentioned here. Okay, and this is true for both subtraction as well as addition. Okay. Now what about matrix multiplication? Because this is something which we will use very often in case of group theory. When we use these matrices to represent symmetry operations, we need to do like two successive operations. So it means like operation A followed by operation B. So when we will try to use matrices to represent these symmetry operations, then these matrices will be multiplied, right? And that's why this is quite important in our context. So there are certain rules for matrix multiplications which are scripted here. So the first one, it concerns the multiplication between a matrix and a scalar. So if you are given any matrix for any order and you are given a scalar and you have to multiply the scalar to this matrix, then it's simply multiplying each element of the matrix by this scalar quantity. Then you get a multiplication. Okay, so for any matrix say B whose elements are B I J, and if you are given given a scalar quantity A, then the new matrix that will form after the multiplication, its elements R I J will be related to A and B I J as follows. Okay, so it's essentially multiplying all the elements of the matrix B by the scalar quantity. So one example is given here, where you can see that 8 is the scalar quantity and you have this 2 by 2 matrix. So 8 is being multiplied with each of the elements. So 8 2 you get 16, 8 6 you get 48, and so on. Okay. So one important aspect of this scalar multiplication with the matrix is its commutative nature. So it doesn't matter whether you multiply the matrix with the scalar or scalar with the matrix. So the order doesn't matter. Whatever way you do, the result will be the same. So that is stated here. AB equals to BA. Now the most important rule here is as follows. So this rule involves the multiplication of a row vector by a column vector. Okay. Now to perform this, the row vector must have as many columns as the row column vector has. Okay. So it says that if I take any row vector, okay, so it's just a row. Okay, that is called a row vector. So you have like one row and n number of columns. So you don't have more than one rows. So this is called a row vector, and a column vector is just you have one column and you can have n number of rows. So only when you can have this multiplication when this row vector has the number of columns which is equal to the number of rows that a column vector has. Okay, so that is shown by an example here. So here this is a row vector that has 3 columns, and it can be multiplied with a column vector that has 3 rows. If I would have 2 rows for the column vector or 4 rows for the column vector, I could not do this multiplication. Okay, so this is very important rule, and this immediately tells you that you cannot have multiplication between any two matrices that has to follow this criterion. So this has been shown by a column vector and a row vector, but this is applicable to the matrix as a whole. So all the other types of matrix multiplication involve the multiplication of a row vector and a column vector. So you can imagine any given matrix of whatever order as as an ensemble of several row vectors or several column vectors. Okay, so in general, if you want to do matrix multiplication, so it will just involve the multiplication of a row vector and a column vector, like we showed just in the previous slide. So specifically in the expression R equals to AB, where A and B are two matrices and R is the resultant matrix of their multiplication, and this the small r's and A and small b, they represents the elements of those matrices R, A and B, which are written in capital letter and in bold font. So here you can see that this Rij equals to A I dot and B dot j, where this A I dot is the ith row vector in matrix A, and B dot j is the jth column vector in matrix B. Now you see that the number corresponding to the column for A matrix is given as a dot, and same dot is given for the the number of row for the element corresponding to B matrix. So these two dots are same, meaning that their numbers are same, and then only you can do the multiplication. So following that, you have an example here where you have taken this A and B, and A is a matrix which has 2 rows 3 columns, while B is a matrix having 3 rows and 2 columns. So you can do a multiplication like this. So the rule of thumb is, when you do a multiplication, multiply one matrix to another, you do it in this way. So first you follow this and you follow this. Okay. Next again you follow multiply with this one. Then you do with using this one, and then again this one. Okay. So you follow like row and then column. Okay, and you have it like one element multiplied to another element, and then you keep doing the multiplication and sum them all together, which is explicitly shown here. So this is the resultant element R11, and this is how you do the multiplication. So 1 to 1 correspondence is here, and ultimately you get the respective values which will act your as the element of the resultant matrix. So you get R11 and R12. So 11, as I said, it follows the first row of the first matrix and multiplies with the first column of the second matrix, and R12 will be the first row of the first matrix multiplied to the second column of the second matrix. Okay, in that way it will keep going, and ultimately you will get the all the elements of the resultant matrix, and ultimately you have a product like this. Now this is interesting, right? You had like a matrix with 2 rows and 3 columns which multiplies with the matrix having 3 rows and 2 columns, and then the product is a 2 by 2 matrix, okay, having 2 rows and 2 columns. So for matrix multiplication to be legal, the first matrix must have as many columns as the second matrix has rows. That you have probably understood by now when we gave the example of the condition of row vector and column vector. If you just extend that to any given form of matrix, then you come to this particular rule which we are talking about right now. So for again, if we state the sentence, so for matrix multiplication to be legal, the first matrix must have as many columns as the second matrix has rows. This of course is the requirement for multiplying a row vector by a column vector, right? The resulting matrix will have as many rows as the first matrix and as many columns as the second matrix. So that's why you are getting this 2 by 2 matrix, because the first matrix had 2 rows and second row matrix had 2 columns. So number of rows of the first matrix and number of column of the second matrix will give you the total dimension of the matrix that is resultant. Okay, so that's about the matrix multiplication. Now there are certain other properties of matrix that we will look at now. One is the transpose of a matrix. Okay, this is again something which is important in our particularly in our context. So the transpose of a matrix is denoted by a superscript t, and sometimes it is also written as a prime, okay, or with a superscript which is small t, but normally we use a with a superscript t, where t is capital letter. All right, so that's the symbol of transpose. Now what is the transpose? So the first row of the matrix becomes the first column of the transpose matrix. So I had say matrix having say 3 rows and 3 columns, okay, or say 3 rows and 2 columns, okay. So this matrix, when I will transpose, it will become like a matrix having 2 rows and 3 columns. So here is one example where A is a matrix having 2 rows and 3 columns, and that when I transpose it, it becomes 3 rows and 2 columns. Okay. So the transpose of a row vector will be a column vector, obviously, and the transpose of a column vector will be a row vector, has to be. The transpose of a symmetric matrix is simply the original matrix. So in symmetric matrix, what we found that any Rij equals to Rji, okay, if Rij and Rji are the elements of the matrix. So in that case, if if you just make the transpose, you are not going to get something new. So for symmetric matrix, the transpose will return you the same matrix. All right. Next, we need to know what is the inverse of a matrix. So in scalar algebra, the inverse of a number is that number which, when multiplied by the original number, gives a product of unity. Hence, the inverse of x is simply 1 upon x, because under multiplication x into 1 upon x will give me 1. Or in slightly different notation, I can write it x inverse. Okay, so x inverse, we are familiar with that already. Now in matrix algebra, the inverse of a matrix is that matrix which, when multiplied by the original matrix, gives an identity. So the notion remains the same. So here in case of matrix algebra, what we have, that I have a matrix, and if I need to find out the inverse matrix, then the inverse matrix will be such that if I multiply this original matrix with its inverse, I will get a matrix which is identity matrix. Okay. So the inverse of a matrix is denoted by the superscript inverse. So it's just an inverse sign. So if I write say a matrix by a capital A in bold letter, so inverse of this matrix will be capital A in bold letter inverse. Okay. So it's implied that A inverse is equal to A inverse A, that is the commute, and the result is identity. And in order to have an inverse, in other words, in order for the inverse of a matrix to exist, the matrix must be a square matrix. That means the number of rows and number of columns must be equal. But the reverse is not always true. So all the square matrices may not have inverse. Okay, in some cases the inverse doesn't exist. Now, before we go to the representation of a group using matrix, we will learn a couple of more things. One is the trace of a matrix. This is something which you will be using throughout the course henceforth, okay, once we go to the representation. So trace of a matrix is the sum of the diagonal elements, okay, of the matrix. So if I look at any given matrix, say on the matrix on your screen here, the sum of 3, 6 and minus 5 will give me the trace of the matrix. Okay, so this has very important consequence, particularly on the context of symmetry point groups and their representations. And you will soon learn that this trace of matrix, particularly certain matrix which can be block factored to a form where you have only the diagonal elements and the off diagonal elements are 0. In those cases, this trace of those matrices will be somewhat characteristic of those particular matrices. That in turn will represent certain symmetry operation, or in case of a group we are talking about, then it will represent the any particular group element. So this trace in the context of group theory, we will be using the term character. Okay, but till now we will just stick to this terminology phrase until unless we go to the representation of group, and we will also learn there why this trace is called a character. Okay, but for your information, you should know that this trace will be actually acting as the character of any representation. Very well. And one more thing I would like to mention here is about the determinant of a matrix. So many of you already know what determinant is. So the determinant is a useful value that can be computed from the elements of a square matrix. So the determinant of a matrix A is denoted as either this term or this symbol. Okay. In the case of a 2 by 2 matrix, the specific formula for the determinant is simply the upper left element times the lower right element minus the product of other two elements. Okay. So if you have a 3 by 3 matrix, then we can determine the value of this whole determinant in this fashion. Okay. So you have this A fixed, and then you find out about this particular part, okay, and then you subtract a part where B is multiplied with the determinant, which is consist of these two terms, okay, on your screen here you can see, and then you do it for the C term. Okay. So in this way you can find out about the determinant of any order. So if you have a square matrix of any given order, you can find the value for that determinant. Okay. So with that we will stop here today, and in the next class we will come back with the representation of the symmetry operations, where we will use this this brief knowledge of matrix algebra that we learned today, and we will use them and try to find out about the representation of the symmetry operations. Thank you for your attention. See you tomorrow.